So let's do a curve sketching example by request. Curve sketching. Somebody wanted to do an example where we, find where it's increasing, decreasing, and then also where the concavity is up and down, and then use that information to draw the shape of the curve. Now, I'm going to, just because I know that the numbers will work out fairly nicely, I'm going to try to do a curve sketching for the function that you see in number 6 there. So you'll see on the paper there are some curve sketching ones that I wrote there for you to try out. I'll leave those for you to try. But let's try to sketch that curve. F of x equals 2x cubed minus 18x squared minus 6. All right? So my strategy is find the critical numbers, do the figure out where it's increasing, where it's decreasing, and then also find any inflection points and figure out where it's concave up versus concave down. And then plot all of those points along with their y values on the graph, and then try to connect the dots with curves of the appropriate shapes. All right. So let's do all that. The first thing I said was find the critical numbers and the increasing, decreasing thing. This involves the first derivative, so you might as well take the first derivative. It should be 6x squared minus 18 times 2, 36x, right? That's the first derivative. And maybe I'll simplify that as much as I can by factoring. I can factor 6x here, and then what remains is x minus 6, all right? So this is the first derivative, as simplified as it's going to get. To find the critical numbers, I'm going to set that equal to 0, and also say when this does not exist, although this one always exists because it's just a polynomial. You don't have to worry about denominator being 0. So anyway, f prime equals 0. This will give me the critical numbers. I'll go 6x, x minus 6 equals 0. 6x equals 0. X equals 0 is 1, and then x minus 6 equals 0. X equals 6 is another. So these are my critical numbers. All right. I saw an interview with a mafia hitman on 60 Minutes once, and that's the way he said numbers. And so I always say it that way now because I like the way he said it. He was talking about all his old buddies and all the crimes that they had committed together, and the guy said, aren't you worried that these guys are gonna come and whack you or something because you're talking about them on TV? And he said, hey, these guys know where I live. If they want to come to my house, they can show up at my house. But if they do, they better come in numbers. I like that line. I thought that was funny. Anyway, those are the critical numbers, all right? I want to use these to do the increasing, decreasing thing. So it's like this. I make a little chart of the first derivative and its signs. The first derivative is 0 at those 2 points, and I'm going to plug in specific values to get the signs in the other 2 points. So to the left of 0, I'll use -1. So f prime of -1. Plugging into the factored version is easiest. At this point, you might be tempted to, get out your calculator, but it's not really necessary to know what the answer is. You just have to know if it's positive or negative. And since this is all multiplied, I can say that's a positive times a negative times a negative. So this ends up being positive because I have 2 negatives there. All right. And then in between 0 and 6, I'll choose +1. So f prime of 1 is 6 times 1 times 1 minus 6, which is positive, positive, and negative. So that's a negative in the middle. And then to the right of 6, I'll choose 7. F prime of 7 is 6 times 7 times 7 minus 6. Those are all positive, so this is positive. All right, so it's increasing and then decreasing and then increasing. That's this will help me draw the shape of the curve. All right, let's also examine the second derivative and do a similar thing to find the inflection points and also when it's concave up versus concave down. So the second derivative. Take the second derivative. First of all, I'm going to take the derivative again of this, although it's easier if you use this formula format because you know this one you'd have to do the product rule. So let's use this format of the first derivative. The derivative there will be 12x minus 36, right? This, I'm going to make a chart of the signs of that. Where is it positive versus negative? So first I find where it's 0 so that I can sort of mark off something on the chart. F prime is 0. 12x minus 36 equals 0. This means 12x equals 36. Divide by 12, x equals 3. So 3 is my marked off point on the second derivative chart. That's where it's 0. Again, I plug in something less and something more, so I'll do f double prime of 0 on the left is 12 times 0 minus 36. This is negative 36, which is negative. And then I'll also plug f double prime of 4. That's 12 times 4 minus 36. That's 48 minus 36, which is positive. So that's a minus and a plus. All right, how are we doing so far? We got the increasing, decreasing chart. And now we have the concavity chart. What should we do next? I'm just about ready to start drawing the graph. Yeah.
Plug back into the original to get the y value?
Yeah, plug these special points. The 0, 3, and 6 are kind of my special points. I'm going to plug them back into the original function to get their y values. So y values. And this one is a bit of a pain in this particular example. And this probably I would... on the test, I would make the function easier because this you're going to, I would say the best way to do this particular step is to use your calculator. But I'm going to say f of 0, remember they are 0, 3, and 6. And maybe I could enlist somebody to help out with the calculation here. I didn't do these numbers ahead of time. I can do 0 though. Remember to plug in, to get the y value, you actually have to plug into the very first original form of the function, not any of the derivatives. All right. So I'm going to plug into here. This is my function. Plugging in 0 is fine. You just get 2 times 0 cubed minus 18 times 0 squared minus 6, which is negative 6. Right? Plugging these other numbers is a pain to do by hand. 2 times 3 cubed minus 18 times 3 squared minus 6. Can anybody do this for me? Yes?
Negative 222.
Is that when you plugged in 6?
Yes.
Okay. I actually did do that one ahead of time. I wrote it down, then I brought the wrong piece of paper to class. But I remember that number, minus 222. I believe this one, actually I don't know. Can someone do that middle one for me? I think it's midway between those two numbers. Should be negative 107. Is that? Anybody agree or disagree? Or maybe 109. I don't really care, but I think it's this. Let's just go with that number.
Negative 114.
14? All right. Something like that. Like I said, on the test, I will cook up the function so that this step right here is easy to do by hand. I would not really expect you to be able to do those numbers. I'm sure you could do them if you have to, but I made a typo right here. This should be 6 squared. I just copied the function wrong. Okay, let's do it then. So I'm going to begin by plotting those particular points first. They are 0, x equals 0, and y equals negative 6. And then x equals 3 and y equals minus 114. And then x equals 6 and y equals this number. So 0 and negative 6 will be something like here, slightly below the x-axis. That's minus 6. Then my next one will be at minus 114 and then minus 222. So this will be over at 3, a point here, and then over at 6, a point here. All right? And 2 of those are critical numbers, and the other is an inflection point. The one in the middle, the 3, is where the concavity changes. The other 2 are critical numbers, which means the slope through these other 2 points is 0 when the curve passes through them. The one in the middle, the slope should not be 0 when the curve passes through it. It's just going to be some other slope. All right? And now, what shape should the curves be? I'm going to summarize our charts that we did before. We had The increasing, decreasing one, so for f prime, it looked like 0 and 6, and it was plus minus plus, I believe. Yeah. And then f double prime was 3 in the middle, and it was minus and plus. Is that right? Yeah. All right. So what I want to see to the left of 0 over here in this area, it should be increasing and concave down. That means it has the frowny shape. That's the concave down. This general shape, but increasing throughout. That means really it's only like this part of that shape. Increasing and concave down. So as it approaches this point, it has that shape, which means it's going to do this, right? Increasing, as you go from left to right, it's going up, but concave down, meaning it has the frowny curvature to it, all right? And then the next region, say between 0 and 3, I'm looking right here in the chart. In terms of the first derivative, it is decreasing, and in terms of the concavity, it is concave down. So it still has the frowny shape like this, but it's decreasing. That means it has this kind of a shape to it. Going down, that is decreasing, and concave down. So it does something like that to get to that point in the middle. All right, and we just keep going. I hope everybody's clear on how I'm getting those shapes. This is a concave down. And you sort of, it has kind of two types of this, right? This one is increasing, this one is decreasing, right? And then there's also the concave up. This is decreasing, and this is increasing. This is concave up, right? Anyway, the next region between 3 and 6 is negative first derivative, that is decreasing, and positive concavity. So decreasing and concave up, that looks like this. So between these 2 points, it has that shape. Like that. All right? And then to the right, all the way to the right, it is positive, positive. That means increasing and concave up. It has this shape here. Like so. That's how it looks. All right. Any questions about that one? So something like this, I hope you would be able to do on the test, apart from those numbers there. Everything else is totally reasonable. And I hope this is satisfying to the person who made the special request. All right. What else do you want to talk about? We can do other examples from any of these sections. Do you want to try a linear approximation, just in case you've forgotten how to do those? Those are a little weird. Even if you remember the formula, which you need to remember the formula, but even so, you'll have to remember exactly how to use the formula. So the one on the page says estimate square root of 38. Maybe we'll try estimate, how about square root of 51 using the linear approximation. All right, so first of all, the formula. Everybody needs to remember the formula. It is this. L of x is the linear approximation of x is f of a plus f prime of a times x minus a, where a is chosen to be some nearby point. So a is going to be something close to 51, where you already know the square root of it. A is a nearby point where f of a, meaning in this example, meaning the square root of a, is already known. What do you want to pick for that? Something close to 51 that you know the square root of? Shout it out. You know the square root of something? Yeah? 49. Yeah, that's a square of something that's close to 51. Right? The square root of 49 is 7. So I'm going to choose a equals 49 because it's close to 51, and I know what the square root of 51 is. I know what the square root of 49 is. All right? In order to use this formula here, so we'll use x equals 51. That's the actual thing that I'm trying to find the square root of, to estimate the square root of, is the 51. In order to plug into that formula, so I have the a and the x, I also need the f. The f is the function that I'm trying to approximate, which in this case is square root of x. I'm going to write as x to the 1/2 because we have to take the square root. Right? The formula also involves, not the square root, we have to take the derivative, f prime of a. So I also want to do f prime of x, 1/2 x to the minus 1/2, which is the same as that, right? That's what x to the minus 1/2 means. It means the square root of x, but in a denominator. Now we should be able to just plug everything into the formula, right? I know what the a and the x are, and I know what f of the x and f prime of x is. So I go L of x, which is 51. I might as well just put 51 in there, equals f of a, which is 49, plus, I'm just copying the formula again, f prime of 49 times 51 minus 49, right? X minus a there. And then you just work out what all this stuff is and simplify it as much as you can. In this type of problem, you probably will be able to simplify it quite a bit. F of 49, this is f right here, square root of x. So this is just square root of 49, which is 7. F prime of 49 means 1 over 2 times square root of 49, which will be, 1 over 2 times 7. And then 51 minus 49 is 2. So that's 7 plus, them 2's will cancel, right? Here and here. So I just get 7 plus 1/7. And that's the answer. This is, apparently the square root of 51 is approximately 7 plus 1/7. Yeah.
And we can leave it at that, right?
Sure. Yeah, you don't need to, is that 50 over 7 if you want? I don't care about that. All right. What else do you want to talk about? We got plenty of time. Yeah.
Can we do a related rates problem?
Sure. A related rates problem. These are kind of tricky for me to just make up on the spot, but I could try. I could just do one on the paper. A cube is growing and its volume is increasing. How about we do number 3, but let's do it with a sphere instead. So a sphere is growing. Now, in order to do this, what I'm about to do, you have to know the formula for the volume of a sphere, which I won't expect you to have memorized, although, if I don't mind saying, I happen to know that formula. The volume of a cube, I would expect you to know. That's much easier. Anyway, a sphere is growing, and let's just do everything exactly the same way that it's on the paper. The volume increases at a rate of 1 cubic centimeter per second. And I want to know how fast is, instead of the side length, let's say the radius, just because that's the most natural thing to talk about. How fast is the radius increasing when r equals 10 centimeters? All right. This is actually kind of realistic in the sense that this is a problem which will arise if you are using like a pump to inflate a balloon. The pump will just spit out a certain amount of area at a certain amount of air at a constant rate. And this will be analogous to this. The volume will be increasing just at some specific rate determined by how strong the pump is, I guess. And then how fast is the radius increasing? So this means as you're pumping up the balloon, how fast will it actually be growing in radial size if the volume is increasing at a constant rate? Let's try it out. Anybody remember I had sort of a few steps to go through in a related rates problem. It involved, first of all, deciding what are the various quantities that are changing in this problem? There's usually two of them, and they're related in some way. That's what most related rates problems are about. So we have two quantities that are changing. I should have written two changing quantities. What are they in this problem?
Volume, radius.
Yeah, the volume and the radius. In this case, I said them by name in the description of the problem. They are the volume and the radius. All right. Next step in a related rates problem is to write down a formula which relates those two things. In this case, it's just the formula for the volume of a sphere, which is the volume is 4/3 pi r cubed. That's the formula for the volume of a sphere. Like I said, I would not expect you to have that specific formula memorized. If I wanted to do this on a test for some kind of other kind of shape, volume of another shape, I would just tell you the formula for it. All right. Anyone remember the next step in the related rates procedure? Yeah.
Implicit differentiation.
Yeah, do the implicit derivative of that formula. This, remember, you take the derivative on both sides of the equation of everything. So on the left, and I'm going to do the derivative like dt, so the implicit derivative d over dt, where t is, the time, which doesn't appear at all in the original formula. But anyway, when I take the derivative on the left side, the v as a variable will become just 1. And then because I'm doing the implicit derivative, I have to multiply times dv dt. So the derivative of v is just dv dt. And then on the right side, 4/3 pi r cubed. So 4/3 pi is just a constant, so that stays like it is. And then when I get to r cubed, the implicit derivative of r cubed shall be 3r squared times dr dt. That's how we do the implicit derivative. All right. And then the last step in the related rates is decide what you want to solve for and then plug in for everything else. So I will say plug and solve is the last step. Those are my 4 steps. Plug and solve. First of all, can I say what are we trying to solve for here?
Radius changing.
Yeah, how fast the radius is changing. Whoa. In this, with this notation in that equation there, what I'm trying to solve for is dr dt, right? That's how fast the radius is changing. That means I got to plug in for everything else. So I need to plug in something for dv dt and something for r, right? Something here and here. Everything else is already a constant. So something for dv dt and also something, come on now, something for r, all right? And hopefully those things are both described in the original question. dv dt means how fast the volume is increasing, and I said 1 cubic centimeter per second. So this is just 1. And then r is the precise radius at the point at which I'm answering the question. And the question is how fast is the radius increasing when r equals 10. So I use r equals 10 centimeters. All right. It's important that you don't prematurely plug in the r equals 10. For instance, like right here, you might be tempted to just use 10 for the r just because, oh, he said r equals 10, right? That would not be correct, though, because then you just have a constant over here. When you take the derivative, everything would become 0, which is not what you want. All right, you have to allow the r, you have to keep in mind that the r is still a changing quantity. It's just that the question is asking something about one particular moment is when you want to answer the question. But you don't plug the r in until the very end. All right, anyway, let's do it. I get, so this formula here, plugging all that stuff in. On the left, it's going to be a 1 equals 4/3 pi times 3 times 10 squared times dr dt, which is what I'm solving for. These 3's will cancel, which is nice. And then I get 10 squared is 100. This is 400 pi on the right side. 1 equals 400 pi dr dt, and then solve for dr dt. 1 over 400 pi. That's quite a small number, isn't it? 1 over something like 1200, right? I said on the paper, at least, I said give your answer with units. What would the units here be?
Centimeter cubed per second.
That's close. It's something per second. You have to think about what that is representing in this problem is the how fast the radius is changing. So what you want to think, what are the units of the radius?
Just centimeters.
Just centimeters, yeah, not cubic. The cubic centimeters is the volume measurement. This is the radius measurement. And it's per second because I'm talking about a rate, something. Sorry, that screen went dark. I don't know why. None of the other ones did. Just look at the other ones. All right. Excellent. What else? We got another 20 minutes or so. Yeah. You want to try optimization? Yes. Those are also difficult for me to come up with on the spot. How about maybe we could try one that's like, there were several on the homework that were like about building the fence, right? Do you want to try one like that? I'll try and invent one about building the fence. How about, I believe, here's one that I saw in the book, but I think I did not put this on the homework. This is about building a fence down by the river. Let's say here's the river, and I want to build the fence like that. This was not on the homework, right? No, okay, good. Let's say I want to build a fence down by the river like that. I hope this isn't a pain to do. I thought about putting this on the homework, and then I decided not to. I never actually worked it out. Let's say that this has some width like that, and then the way that the river goes, this is going to be some height here, and then this height will be 2y. Just because of the slope of the river there. I think this makes sense. And then the question is, which dimensions give the most area? Using, let's say, I don't know if this number is going to work out nicely, but let's just say 100 feet of fence. Actually, I'm going to say 300 feet, because I think that number will work a little bit nicer. All right. So, for our optimization problem, first we want to decide what is the thing I'm trying to maximize or minimize. This is usually obvious from the question. In this case, it is the area, because I said what dimensions will give me the most area. So what I'm trying to do here is maximize the area. Next step is, I hope you remember the general process for optimizations. The next step would be to write a formula for this thing, the area in this case, using a single variable. This is usually the hard step of this problem. Write a formula for the area using a single variable. Maybe I will start by using two variables. I have x and y in this problem, right? Let's try to write a formula for the area using both x and y first, and then I will try to sort of simplify it. So what we have here is really like a trapezoidal shape. did I say 2y over there? Or?
Yeah.
Yes, 2y, okay. What is the area of that? There's a formula for the area of a trapezoid that I don't know if you remember, and actually I would say maybe it's not even very useful in this problem. The way that I would look at this shape and find its area would be, this looks like to me a rectangle on the bottom with a triangle stacked on top of it. That to me seems like the most sensible way to think of this area. You could use some kind of formula about the area of a trapezoid, but no need, right? If we do that, then of course the whole left side is length 2y, but can we say what each of these little lengths are? Like what's that height on the bottom there? It's y. Yeah. If I drew my picture right, this should be y because I made that rectangle, which means the other one is also y because they add up to 2y. All right. So now we should be able to add up these areas. The lower area is a rectangle, which is dimensions x and y. So this area is x times y. And the upper area is a triangle with dimensions, the height is y and the base is x. So that would be 1/2 xy. Right? You could also think that that triangle up top is actually half of another rectangle, which is x by y. So it's 1/2 xy. All right, anyway, the total area here will be xy plus 1/2 xy. Right? That's the bottom part plus the top part. This is a little tricky. I don't know if I would expect you to do that on the test. Maybe that's not so hard. I don't know. A little tricky. I don't know if you feel that's tricky. And you could actually add this up, right? xy plus 1/2 xy is really 3/2 xy, isn't it? So this is the area. Now, really, I would like a formula for the area in terms of one variable. That's necessary in order to solve the optimization problem. How are we going to write this in terms of only one variable? Let's just write it in terms of x. Any ideas? Yeah?
We know the perimeter is 300 feet, so...
Right. Yeah, so that's the other piece of the information which I did not use yet is this, 300 feet of the fence. So I can set up another formula involving the fence length. It is 300 equals, what's it going to be?
x plus 3y.
X plus 3y. Yeah, the total fence length here, it's kind of, I suppose it's the perimeter, but you don't count the riverside. It's this plus this plus this. So 2y plus x plus another y. The y's add up to 3y and 1x. So 300 equals x plus 3y, right? This is why I changed my mind to 300 rather than 100, because I'm about to divide by 3. I'm going to solve for y in terms of x. So it's going to say 3y equals 300 minus x, divide by 3, y equals 100 minus 1/3 x. And this we plug into the formula for a, and we end up with a formula in terms of x only, which is what I wanted. So I'll write a of x is 3/2 x times y, which is 100 minus 1/3 x. That's the hard step usually, is finding the formula in terms of a single variable. We have to go through not a lot of hard math work really, but in this case you have to do some somewhat clever geometry up here. All right, now we are just going to do the absolute extrema thing to this. So this will involve taking its derivative. So I'm going to distribute there just so that the derivative will be easier. Distribute 3/2 x times 100. That's, isn't that 150x, I think? And then minus 1/3 times 3/2 is 1/2, like that. This is a of x. A little simpler. All right. We also need to say what the smallest possible and largest possible values of x are, because we're going to find the absolute extrema. So we want the interval of allowable x's. This might be a little messy in this example, I'm not sure. What you want to look at is this formula here, which tells you how x and y add up. And by looking at this, you can more or less say what the smallest and biggest possible values for x would be. So when I think this will be fine. It seems to me the biggest possible x value would be when the y is 0, you get x equal 300. It couldn't possibly be bigger than that, right? Although even that is not really possible given the picture we're looking at. Yeah, maybe it is. Anyway, I'm going to say that the biggest possible is x equal 300. And then the smallest possible would be when it's all y's and no x. That would be x is 0. So the smallest possible would be x equals 0. All right. Even these might not technically be possible, but we just need some kind of finite range to put the x's in. All right. It can't possibly be more than 300, and it doesn't make any sense at all for it to be negative. Okay, now we are ready to actually do the absolute. In this case, I want the maximum, right? The maximum area. Although when you're doing this, you end up finding the minimum also. This involves, the absolute minimum and maximum. You find the critical numbers by taking the derivative. So I'm going to do a prime of x. The function is right here. This is an easy derivative. Did I mess up? Sorry, when I distributed, this should be an x squared here. Sorry about that. I hope you noticed. I multiplied 3/2 x times 1/3 x. 1/2 x squared. Anyway, take the derivative of that. It's 150 minus 1/4 x. All right? Find the critical numbers. You set that equal to 0. I go 150 minus 1/4 x equals 0. 150 equals 1/4 x multiplied by 4. X is 600. All right? So this is a critical number. Yes?
When you
Did I mess it up?
derivative of 1/2 x squared.
Oh yeah, I messed that up. Thank you. 600 is outside the range, which should disturb you. Yeah, when I did this derivative, 1/2 x squared, it's just x, right? Thank you for that. Sorry about that. So no 1/4 there. No 1/4 here. No 1/4 here. That's the critical number. X equals 150. Sorry about that. I'm trying to get it in before time runs out, but I think we'll be fine. All right, what next? We should check the y values at the critical number, which is that, 150, plus at the two interval endpoints, and choose the maximum out of that. So the y values, or I guess they are the values of a, right? I'm going to do a of 0, a of 300, those are the two endpoints, and then also a of 150, all right? A of 0 is, forgot my formula for a, is here, the one with the square in it. Maybe somebody could help me with the numbers on the, I think the endpoints are both going to be zeros. A of 300, this is 150 times, yeah, that's going to be 0 also. This one is going to be some very special number. 150 times 150 minus 1/2 times 150 squared. Actually, that is 150 squared minus 1/2 of 150 squared. This will give you 1/2 of 150 squared. Can anybody do that number for me?
11,250.
11,250. All right, thank you. Anyway, that's the maximum, right? You can tell that's the maximum because the other two are 0. So this is the maximum. All right, we're pretty much done. I don't remember what the specific question was at this point. It says, which dimensions give the most area? Okay, so the dimensions, the most area happens when x equals 150. And I should also say y, because I said, tell me the dimensions which make this work out. What's the y going to be? If x is 150, you have to just go back to this thing, right? 300 equals x plus 3y. So to solve for, or actually, it's a little easier. Where's the one when I solved it for y? y equals 100 minus 1/3 x. So I will say y is 100 minus 1/3 x. This is 100 minus 1/3 times 150. This is 100 minus 50, which is 50. All right? So this is my answer. X equals 150, y equals 50. That worked out pretty well, I think. And one thing to notice is this number here actually wasn't really relevant in the answer of the question that I was asking. So even if you didn't have a calculator, you didn't really have to write this number down, right? You could have identified that that is the maximum because its only competitors were both 0, so this has to be the maximum. All right. I'm pleased with that one. You want to hear an interesting fence building math problem? This is something I only recently became aware of this. This is a question that people have been, it was first asked like over 100 years ago, I think. If you have a circular fenced-in area, this is called something like the goat in a fence problem or something. You have a circular area and a goat on a little rope here. Here's the goat. This is a goat. Tied to the rope. All right. In this picture, the goat can. The question is about how much of the area inside here does the goat have access to? And in this picture, it's something like this. The goat's sort of capability is to roam like in a little circular area within that circle, right? Problems about this are not so hard to solve, but a more interesting problem is when the goat is on the outside of a circular thing. Here's the goat now. That's the goat, right? Now his area that he can possibly roam in is some sort of strange shape that looks, if I were to exaggerate the shape, it looks something like this. It has these weird bulges in it, sort of, because the goat, you might think whatever the length of this rope is, that's how far over this way the goat can get. But actually, the goat can't quite go that far because the rope has to wind around the edge of the circle as the goat. Anyway, the problem that was first posed over 100 years ago is how long should the rope be so that this area that the goat has access to is 1/2 of the area of the circle? And the answer to this problem is not known. That's the interesting fact. It seems like maybe a complicated geometry problem, but it certainly seems like something that you could figure out, or that somebody could figure out. The answer, there is no known formula for this answer. You can try to estimate this value using numerical analysis methods, but actually nobody knows. If you wanted to say write it in terms of pi or square roots or what, nobody knows what the true answer is. Interesting little fact, I think.